On a quiet morning in 1975, Chinese officials evacuated an entire city. Hours later, a massive earthquake leveled it. It looked like the impossible had happened. Scientists had predicted an earthquake. Then, 1 year later, in the same region, a quake killed over 200,000 people. No warning, no evacuation, no prediction at all. So which was it? Can we predict earthquakes? Or was that one lucky guess in a game we still don't understand? Today we're digging into one of the most frustrating unsolved problems in modern science. Not because scientists haven't tried. Billions of dollars, decades of research, and some of the sharpest minds in geology have all gone into this question. And yet, right now, in 2026, no government on Earth can tell you exactly when or where the next big earthquake will strike. We're going to find out why, and what that really means for the millions of people living on top of fault lines right now. To understand the problem, you have to understand what's actually happening beneath your feet. The Earth's outer shell isn't one solid piece. It's broken into massive plates, drifting slowly over a hot, shifting layer beneath them. Where these plates meet, they don't glide smoothly. They catch. They lock. Stress builds up along the fault, sometimes for decades, sometimes for centuries, like a rubber band being stretched tighter and tighter. Eventually, something gives. The rock breaks, energy releases in seconds, and the ground shakes. That part, scientists understand well. The plates, the stress, the eventual rupture, that's basic plate tectonics, and it's been solid science since the 1960s. Geologists can map fault lines with incredible precision. They can measure how fast plates are moving, down to the centimeter per year. They can even estimate roughly how much energy is stored in a given fault. In many ways, we understand earthquakes better than almost any other natural disaster. The real mystery isn't why earthquakes happen, it's when. Here's where the first big discovery comes in. In the early 20th century, seismologists noticed something promising. Before some earthquakes, the ground would tilt slightly. Water levels in wells would rise or drop. Animals, according to old reports, sometimes acted strange. It seemed like the Earth was giving warning signs, and researchers got excited. If a fault could tell you it was about to break, prediction wasn't a fantasy. It was just a matter of listening closely enough. That optimism reached its peak with Parkfield, California, a small town that would become one of the most studied patches of ground on the planet. Scientists noticed something remarkable. Earthquakes seemed to strike that same stretch of the San Andreas Fault roughly every 22 years, almost like clockwork. 1857, 1881, 1901, 1922, 1934, 1966. In the 1980s, researchers made a bold move, one that would define the entire field for decades. They predicted the next Parkfield earthquake would happen by 1993. They wired the ground with instruments, installed some of the densest monitoring equipment ever deployed, and waited for the moment that would prove earthquakes could finally be forecasted with precision. And then, nothing happened. Not in 1988, not in 1993. Years passed. The earthquake didn't arrive until 2004, over a decade late, and by the time it hit, most of the world had stopped paying attention. The pattern that seemed so reliable simply broke. That failure taught scientists something uncomfortable. Earthquakes don't run on a schedule. The mini-signals people had hoped were reliable warnings, the tilting ground, the changing water levels, turned out to be inconsistent. Sometimes they showed up before a quake. Often, they didn't show up at all. And sometimes they appeared with no earthquake following them whatsoever. The Earth wasn't whispering a countdown. It was, at best, throwing out noise that only sometimes overlapped with the signal. So why is this so much harder than predicting a hurricane or a volcanic eruption? This is where it gets genuinely fascinating. Hurricanes form over days. Volcanoes usually give weeks of warning through swelling ground and gas emissions. Earthquakes are different because the actual trigger, the final microscopic slip that turns built-up stress into a catastrophic rupture, happens deep underground, out of reach of almost any instrument we have. You're trying to predict the exact moment a piece of rock several miles down finally loses its grip, and that moment can depend on factors so small and so localized that even the best equipment can't reliably catch them in advance. Now here's the twist that changes the whole conversation. For a long time, some scientists believed better sensors and more data would eventually crack the problem, that prediction was simply a matter of technological patience. But research starting in the 1990s pointed to something far more unsettling. Some scientists began to suspect that earthquakes might be fundamentally mathematically unpredictable at the level of precise timing. Not unpredictable because our instruments aren't good enough yet, but unpredictable because of the chaotic nature of how stress and rock fractures actually interact. Think of it like trying to predict the exact snowflake that triggers an avalanche. You can know the slope is unstable, you can know it's overloaded with snow, but which single flake causes the whole thing to collapse and at what precise second? That's shaped by tiny, chaotic variables that are, for all practical purposes, impossible to fully measure or model. Many researchers now believe earthquake rupture may behave the same way, governed by small-scale friction and rock conditions that are simply too complex and too hidden to observe in real time. This doesn't mean scientists have given up, far from it. What's changed is the goal. Instead of chasing the dream of predicting an exact date, hour, and location, which is what the public usually imagines when they hear earthquake prediction, the field has shifted almost entirely towards something more achievable, forecasting probability and detecting the earliest seconds of a quake that's already begun. Earthquake forecasting looks at the long-term picture. Scientists study a fault's history, how much stress has built up, and how often it has ruptured in the past. From that, they can say something like, there's a 70% chance of a major earthquake in this region within the next 30 years. That's genuinely useful for building codes, insurance planning, and infrastructure decisions. But it's a probability over decades, not a warning you can act on tomorrow morning. The other approach is where things get exciting, and it's already saving lives today. It's called early warning, and it doesn't predict earthquakes at all. It detects them the instant they start. When a fault ruptures, it sends out two types of seismic waves. The first, called P waves, travel fast but cause little damage. The second, S waves, arrive seconds to tens of seconds later, and they're the ones that shake buildings apart. Sensor networks like Japan's and California's ShakeAlert detect that initial P wave and send out an alert before the damaging S waves arrive. It's not much time, sometimes just a few seconds, sometimes closer to a minute if you're farther from the epicenter. But those seconds are enough to stop surgeries, open elevator doors, halt trains, and get people away from unstable structures. And this brings us to the biggest reveal of all. Earthquake prediction, in the sense most people imagine, an exact date and location announced in advance, like a weather forecast for the ground, may never be possible. Not because scientists lack effort or intelligence, but because the Earth itself may not follow a predictable script. The rupture point of a fault could be so sensitive to microscopic conditions, invisible even to our most advanced sensors, that true prediction sits beyond the reach of any future technology, not just today's. Some scientists compare it to weather beyond about 2 weeks out, a system so chaotic that added precision stops helping past a certain point. Earthquakes may be the geological version of that same wall, but here's the part that actually matters for your safety and mine. The absence of prediction doesn't mean the absence of protection. What science has built, instead, is arguably more valuable. Buildings engineered to flex rather than collapse, early warning systems that buy precious seconds, and long-term probability maps that shape how entire cities plan for the future. Japan, California, Chile, and other high-risk regions have leaned into this reality, not fought it, and it's saved countless lives. So the next time you hear about an earthquake striking without warning, remember, that's not a failure of science. It's a boundary of nature itself, one that researchers have spent over a century mapping the edges of, quake by quake, failed prediction by failed prediction. And in a strange way, understanding what we can't predict has taught us more about protecting ourselves than a perfect prediction ever could. Maybe the real lesson isn't that we failed to tame the Earth's unpredictability, it's that we learned to live wisely within it.